Okay, just a few more topics to talk about in the context of gases. And the next topic is the change equation, okay? So essentially, you'll see some types of problems where multiple pressures, multiple volumes, multiple temperatures, and or multiple moles are given. And it doesn't look like there's a reaction going on or anything. It just looks like you're changing the conditions of the gas. If I change one of these, the other ones will be affected as well, okay? So essentially, we need a way of approaching this. Now, when you do these problems, there are alternate approaches where you could say, for instance, use the ideal gas law twice. But there's a quicker way, and we're going to refer to this quicker way as the change equation. No matter what changes I make to P, V, T, and N, which are part of the ideal gas law, R won't change, right? R is a gas constant. It's constant no matter what. So before my change, I have R, and after my change, I have R, and they're equal to each other. That's kind of like not really useful on face value until you realize that R is equal to PV over NT. So if I take the ideal gas law and I solve it for R, right, I have PV over NT. So R before the reaction, sorry, R before the change is equal to R after the change. So PV over NT before the change is equal to PV over NT after the change, right? So if I'm making, a compression, a change in volume, or I'm changing the pressure, or I'm changing the temperature, while keeping some things constant, sometimes not, then I can set PV over NT equal to PV over NT. Now we get real lazy again. We don't like to write before, and we don't like to write after. So what we do instead, and this is our starting point when we identify that we have to use the change equation, is we write P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. Okay. So just like everything, let's do an equation to make sure that we can, let's do an example using this equation. So we can make sure we identify when we do have to use it, and then we make sure that we enact things appropriately, okay? We still have to make sure that we put the correct units in there, so nothing really changes about that. So to be sure that you do things correctly, always use your ideal gas law units. Always use the units inside R. Let's take a look at example from your slide show. So this is chapter 9 PowerPoint, and let's look at slide 2. All right. Now, chapter 9's PowerPoint slide 2 will give you some information about a gas, and the gas is undergoing a change. And essentially what you have is a sample of gas. And this actually is important to us eventually, okay? And the sample of gas is undergoing a change, and essentially what you have is an initial volume that I'm going to label V1, which is 9.10 liters, and associated with that volume is a T that's equal to 198 degrees Celsius. Okay. You're making a change. If you read the wording of that problem, that gas is changed. And you're changing the temperature to produce a different volume. And your target volume is 2.50 liters. You're asked for the temperature that gives you that 2.50 liters. And you're also told that P is constant. Now, keeping one or two variables constant is common with these sorts of problems, okay? But let's do our identification step first so we understand what's occurring here. We talk about just a simple sample of gas. We don't see anything about reactions going on. And notice what you're given, multiple V's, and you're asked to relate multiple T's together. Those indications tell us that our starting point is P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. Okay. Now we analyze the problem. There's essentially 8 variables here. And whenever you try to do a problem here with one equation, we need to know all of these, all right, except for one. Remember, if we have one equation, we just need one unknown to be able to solve for it, right? So let's start to go through the wording of the problem. A sample of gas. This actually tells us something. There's no wording in the problem associated with adding moles of gas or subtracting moles of gas. We have one sample of gas, and pretend it's in a balloon or some other sealed container. We have a fixed number of moles. So that one sample of gas has a certain number of moles. And if you don't see anything about putting moles in or taking moles out, then this N2 is the same as N1. So if those guys are equal to each other, they're on opposite sides of the equation in the same spot, they cancel out. Along those lines, okay, we can go to the fact that in this problem it is stated that pressure is constant. So what does that say about P1 and P2? That tells you that they are equal. So they're in opposite sides of the equation and on the same spot, so those also cancel. Well, now we can do our checklist thing, all right? And we can make sure that we have enough information where we can feed it into this form, all right, and only have one unknown. So I've identified a V1, I've identified a T1, I've identified a V2, and I'm trying to solve for T2. So do I have an equation with one unknown, right? Where everything else is known? Well, once I do that canceling, the answer is yes. One equation with one unknown means that I can solve for that one unknown, right? Now, before we start to substitute values in, remember, units matter. And hopefully you can look at the information in this problem and recognize there's one change that we definitely need to make before we start this process. And whenever we use temperatures, in anything related to gases, we are never going to use degrees Celsius. And we will get the completely wrong answer if we use degrees Celsius. Remember, this came from R equals R. And what's the temperature unit inside R? Kelvin. So the first thing we're going to have to do is convert this to Kelvin. And what we get is 471.15 Kelvin with 3 significant figures. Because we know that degrees Celsius plus 273.15 will give me, right, my Kelvin temperature. Okay, so let me just rearrange this and see what we have, and then let's do the substitutions together, and then let's analyze the result. So essentially, after we cancel things, we have V1 over T1 is V2 over T2. So now we're going to solve for T2. So let's multiply both sides by T2. T2, V1 over T1 equals V2. And then let's isolate T2 by taking this fraction and multiplying both sides by its inverse. So T2 is equal to V2, T1 over V1. Now these values I know, right? V2 was 2.50 liters. V1 was 9.10 liters. And T1 in the correct units in Kelvin was 471.15 Kelvin. So now we have everything set up. Oh, sorry, I ran out of room there. Let me just make sure you see this. Right here, we're going to write 471.15 Kelvin. Okay, multiplicative factor. This is this value right here. So now we can plug this into our calculator, and what we get for T2, notice liters is going to cancel with liters. My units that I'm left over with are Kelvin. The T2 that I get is 129.44 Kelvin. Okay, now we would round that to 129 Kelvin. Now let's make sense of our answer. So one thing we can always do at the end of these problems is make sure that our answer makes sense, okay? So let's kind of review where we started with. We started with a volume that was 9.10 liters at a temperature that was 471 Kelvin, right? We ended up with a V2, okay, a V2 that was 2.50 liters. Yeah, 2.50 liters. All right. At a T2, that's 129 Kelvin. So how does this make sense? We had a big volume at a higher temperature. And then we cooled this gas down. And we kept the temperature, right? Oh, sorry, we kept the pressure constant. But we cooled this down to a lower temperature. So what happened inside that container, right? Inside that container, the gas was moving slower. Now it was moving slower, but the pressure was constant. So if I have this piston, right, and I have a certain pressure that's based off the strikes on that surface, okay, and then I go to a smaller volume, so I squish it down, but I want the same hits on that surface, what's the only way to do that? It's by making things move slower, so that these gas particles are moving slower so that they strike this surface at the same frequency as when there was more room, but they were moving faster. So the fact that the volume went down as the temperature goes down makes perfect sense to us, and it validates this answer as the correct answer and something that we should be confident in. So at the end of any of these change equations, and they're all sort of different, any of these problems that involve this, okay, just make sense of your answer. It won't always be this nice where two of these variables cancel out, okay? But anyway, you start with something with 8 unknowns. You try to find a way to either cancel stuff or fit 7 bits of information in there, and you solve for the last one, paying attention to correct units, and then again, you should have confidence that you can do these problems correctly, right? The next video is going to deal with the last topic in this gas chapter, and that has to deal with mixtures of gases.